faster than the fabric of space-time can keep up with it, and it'll just rip, and I'm terrified by that. Currently, our night sky is experiencing significant changes. Astronomers worldwide are expressing concern over the future of Polaris, the North Star, with renowned expert Neil deGrasse Tyson confirming the possibility of its imminent explosion. Polaris has long been a steadfast guide for stargazers, navigators, and astronomers alike. Its constant presence in the night sky has provided a reliable reference point for centuries. However, recent research presented by the esteemed Royal Astronomical Society in September 2023 has raised doubts about its fate, suggesting that it may be on the verge of a cataclysmic event. Understanding the importance of Polaris requires delving into its characteristics. Situated in the constellation Ursa Minor, also known as the Little Dipper or the Small Bear, Polaris stands out as a moderately bright star. Its size surpasses that of our Sun, classified as a yellow-white supergiant with a radius estimated to be about 40 times greater. Contrary to popular belief, Polaris is not a singular entity but rather part of a complex triple star system comprising Polaris A and Polaris AB as primary stars. It appears as a single star to the naked eye. Additionally, it has a third companion, Polaris B, orbiting the binary pair. The gravitational interactions among these stars influence their orbits and characteristics, contributing to the complexity of their dynamics. Despite its apparent stability, Polaris is subject to fluctuations in luminosity and behavior due to these intricate interactions. However, the precise mechanisms governing these phenomena remain elusive to astronomers. One striking aspect of Polaris is its distance from Earth, approximately 323 light-years away. Consequently, the light we currently perceive from Polaris originated over 3 centuries ago. This temporal delay means that if Polaris were to undergo a dramatic event such as an explosion, we would only become aware of it centuries after the fact. Historically, Polaris has held immense cultural and navigational significance across civilizations. Its fixed position near the celestial North Pole made it an invaluable navigation aid for ancient mariners, guiding them across seas and lands. Furthermore, its symbolic importance transcends cultures, representing constancy, guidance, and stability in various mythologies and folklore. From an astronomical perspective, Polaris's stability provided astronomers with a reliable reference point for observing and studying the motions and patterns of celestial bodies. In summary, the potential fate of Polaris poses not only a scientific curiosity, but also holds cultural, navigational, and symbolic implications that resonate across civilization. Polaris, known as a Cepheid variable star, exhibits periodic fluctuations in its brightness. This characteristic has been instrumental in advancing our understanding of stellar properties and the nature of variable stars. The regular pulsations of Polaris have played a crucial role in determining cosmic distances and calibrating astronomical instruments. Typically, Cepheid variable stars like Polaris display a predictable pattern of pulsations. However, recent observations have revealed deviations from this expected behavior. Instead of following its usual pulsation cycle, Polaris has shown irregular and unpredictable variations in brightness, alternating between periods of dimming and brightening. This unexpected behavior has perplexed astronomers, prompting a closer examination of Polaris's pulsation cycle. Unlike its typical pulsation pattern characterized by regularity and predictability, the current erratic behavior suggests a departure from its normal state. Scientists have raised concerns that these irregularities may indicate Polaris is approaching the end of its life cycle. The anomalous behavior of Polaris aligns with patterns observed in stars nearing the end of their evolutionary journey. Such behavior often precedes a significant stellar event such as a supernova explosion. The progressive elongation of Polaris's pulsation period, traditionally stable in its cyclic dimming and brightening, hints at underlying changes within the star system. One notable observation is the gradual increase in Polaris's pulsation duration, with an annual increment of approximately 4 or 5 seconds. While seemingly insignificant, this deviation signifies significant changes occurring within the star. Astronomers have proposed various explanations for Polaris's irregular behavior. Some suggest that gravitational interactions between the constituent stars of the Polaris system may influence the star's atmospheric conditions, directly impacting its pulsation patterns. However, others remain unconvinced and speculate that Polaris may be nearing the end of its life, mirroring the behavior of Betelgeuse, another prominent star exhibiting irregularities in luminosity. The resemblance between the fluctuations observed in Polaris and Betelgeuse is intriguing, suggesting common underlying mechanisms. Cepheid stars in their twilight stages often undergo erratic changes in luminosity as they approach the culmination of their stellar evolution. NASA's heightened interest in Betelgeuse's irregular behavior contrasts with the comparatively limited scrutiny directed towards Polaris. While Betelgeuse has garnered considerable attention due to its potential for a supernova explosion, similar vigilance regarding Polaris's irregularities has yet to be officially announced. Cepheid stars progress through various phases in their evolutionary cycle. Beginning as relatively cool and dim objects, they evolve into main sequence stars where nuclear fusion sustains their stability for billions of years. As their hydrogen fuel depletes, Cepheids transition into red giants characterized by a significant increase in temperature and brightness. The red giant phase culminates in a dramatic supernova explosion, leaving behind a compact white dwarf. Analysis of Polaris's irregular pulsation suggests that the star has entered the stages of helium depletion, a characteristic feature of Cepheid stars nearing the end of their life cycles. Helium depletion triggers erratic pulsations, causing fluctuations in brightness and indicating the star's progression towards the final stages of its evolution. Despite these observations, conclusive evidence of Polaris's impending supernova remains elusive. Astronomers continue to monitor and interpret the star's behavior in pursuit of understanding its ultimate fate. If Polaris were to undergo a supernova explosion, it would likely produce a spectacular display in the night sky. The sudden increase in brightness could outshine even the Moon and alter the appearance of familiar constellations such as the Big Dipper or Ursa Minor. Fortunately, despite the potential for a dramatic stellar event, Earth would likely remain unharmed due to Polaris's considerable distance from our planet. When considering the aftermath of a potential Polaris supernova, it's essential to understand that unlike giant stars, which often culminate their lives in such explosive events, Polaris is unlikely to follow suit. Typically, when a massive star undergoes a supernova, a dramatic collapse of its core triggers a violent explosion. This phenomenon disperses heavy elements and may lead to the formation of neutron stars or black holes. However, Polaris, being approximately 5 times more massive than the Sun, lacks the necessary mass to end its life in a supernova explosion. Supernovae are broadly categorized into Type 1 and Type 2 events. Type 2 supernovae occur in massive stars with complex layers, where the core collapse initiates a powerful outward shock wave resulting in a burst of light and energy visible across vast distances. On the other hand, Type 1 supernovae occur in binary star systems involving a white dwarf, which undergoes a nuclear fusion reaction leading to a sudden explosion and the release of immense energy. Following a supernova event, the collapsed core of a star may birth either a neutron star or a black hole. Neutron stars are incredibly dense, encapsulating up to 3 times the mass of the Sun within a confined space comparable to a modern-day city. Black holes are infinitely dense, exerting gravitational forces so strong that even light cannot escape. In contrast, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This process, known as a planetary nebula, results in a serene conclusion to its stellar evolution as it becomes a small, extremely dense remnant. A white dwarf is the remnant of a low or medium-mass star that has depleted its nuclear fuel. Remarkably dense, it possesses the mass of the Sun, but is compressed to the size of Earth. Once Polaris completes this transformation, its remnants will no longer be visible from Earth in the same manner as observed today. Comparing the anticipated effects of a Polaris event to historical supernova occurrences such as SN 1054 or SN 1987A offers valuable insights into its potential aftermath. Evaluating similarities in luminosity variations, elemental ejections, and impacts on surrounding celestial environments provides a basis for understanding the potential consequences of a Polaris event. Contrasting anticipated outcomes with observed supernova events is crucial for predicting the fate of Polaris. Recent supernovae such as SN 2011 Fe or SN 2014 J provide valuable data for comparison. Analyzing their light curves, spectra, and remnants can offer insights into potential evolutionary stages of Polaris's remnants. By examining differences in mass, composition, and ejected material, scientists can project characteristics of Polaris's burst and its resulting celestial remnants. Furthermore, comparing Polaris's anticipated burst with other supernova phenomena involves analyzing the evolutionary paths of stars leading to their explosion. Scientists aim to assess the mass, metallicity, and evolutionary stages of stars pre-supernova, thereby understanding potential disparities or similarities in their explosion mechanisms. Another critical area of study involves evaluating the pulsational variability of stars nearing their end stages akin to Polaris against observed supernova precursors. By gauging similarities or deviations in their pulsational behavior, astronomers can enhance understanding of the burst mechanism. Despite meticulous observations and extensive analysis, astronomers find themselves puzzled by the irregularities observed in Polaris's behavior. Predicting the end of a star's life is challenging, and the perplexing nature of Polaris's irregular pulsations eludes a complete explanation. The enigmatic behavior exhibited by Polaris underscores the criticality of deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding its irregular pulsations, recognizing the necessity to unravel the unique conditions triggering this anomalous behavior. The looming uncertainty surrounding the potential burst of Polaris poses substantial concerns. Recent revelations from the Royal Astronomical Society have highlighted a new area demanding intense scrutiny and research. Ultimately, only time will reveal the true nature of Polaris's fate. In the meantime, advancing comprehension of the underlying mechanisms shaping its irregularities is paramount. However, if Polaris were to undergo a catastrophic event, the loss of this crucial reference in the night sky could significantly impact astronomical assessments, necessitating recalibration of ground instruments. The anomalous behavior exhibited by Polaris has unveiled a realm of uncertainties in the astronomical domain. Its impending burst calls for heightened vigilance, dedicated research endeavors, and a concerted effort to grasp the unique celestial intricacies shaping its erratic behavior. Thanks for watching. Don't miss this video you see on your screen right now. It's truly unbelievable.